if thermodynamics is the subject dealing with the conservation of energy principles and the generation of entropy in the thermodynamic universe in general, in the subject heat transfer, we would have to deal with the rate at which heat energy is being transferred between any two bodies or within a body due to temperature difference. As we know earlier in the Clausius statement of second law of thermodynamics, which says that heat will always flow from high temperature to the low temperature, that is called second law of thermodynamics. The temperature difference is the driving potential for the phenomena called heat transfer. Basically, this phenomena would happen in three different modes or fashions, namely conduction, convection, and by radiation. Now let me elaborate about these three phenomena individually. Considering conduction, heat transfer. Conduction is the mode of heat transfer which generally takes place inside the solids due to temperature difference by free electron transfer and also by molecular lattice vibration. The example to this phenomena called conduction could be given like this. I take a metallic rod. One end of which is kept over a flame or a source of heat. And other end I am holding with my hand. After some time, the end whichever I am holding becomes hot and I would not be able to hold it anymore further because heat energy has conducted from this high temperature to the low temperature. This is the direction of heat transfer Q prescribed by the Clausius statement of second law of thermodynamics. Heat will always flow from high temperature to the low temperature. Therefore, the temperature difference is the driving potential for this heat transfer phenomenon. How this heat energy is being conducted through this metallic rod? In the metallic rod, there are molecules which are very closely kept. Molecular lattice structure would be there inside the rod. The molecules which are in the vicinity or locality of high temperature will receive the energy. They start vibrating with certain frequency. It is a vibration. It is a vibration phenomenon. So while vibrating, because they have received the energy, they started vibrating with high frequencies and high amplitudes. They would be transferring this vibrational energy to the neighboring molecules. The neighboring molecules also begins to vibrate with a greater frequencies and amplitudes. That in turn would transfer that energy to the next neighboring molecules. That is how the heat energy is supposed to be transferred or conducted. Not only by that phenomenon, the free electrons which are present in the outermost orbits of the atoms of the molecules would receive the heat energy and they jump from one molecule to the next molecule and give that energy to the free electron present in the next molecule outermost orbit. That would in turn receive the energy and give the and jumps from that molecule and goes to the next molecule. Like that, there is a free electron transfer, which is also called as electron gas. I can say roughly 75 to 80% of heat energy is being conducted because of this free electron transfer. particularly inside the metals. Why do metals are good conductors of heat? Since they have free electrons in the outermost orbits of atoms of molecules. That is the reason why all the metals are good conductors of heat. And also metals are also good conductors of current electricity. Why the metals are good conductors of electric current and as well as good conductors of heat? Because they possess free electrons in the outermost orbits of their atoms. So I can define conduction as conduction is the mode of heat transfer which generally occurs in solids due to temperature difference by molecular lattice vibration and also by free electron transfer. Around 80% by electron transfer and 20% by lattice vibration. The reason why good electrical conductors are also good heat conductors because of the presence of free electron transfer. All metals are good conductors of heat. Example, all metals are good conductors of heat. Example, copper, silver, steels, aluminium, etc. Conduction would also occur in gases due to molecular momentum transfer during collisions of molecules present in gas. For example, if we take two plates, one is at high temperature and other is at low temperature. The gap between the two plates is filled with a gas carrying so many molecules, so many crores of millions of molecules present between the two plates. The molecules which are present in the vicinity of the high temperature, they receive that energy and keeps moving with higher velocities, because the RMS velocity of molecule of gas is directly proportional to the square root of absolute temperature of the gas from kinetic theory of gases. From kinetic theory of gas, RMS velocity C bar is directly proportional to the absolute temperature, square root. So when the high temperature molecules start moving or keeps moving with a higher RMS velocities, when they collide with the relatively slow velocity molecules at low temperature, they transfer that momentum when they collide with the low temperature, low velocity molecules. So the low temperature, low velocity molecule receive that momentum and they keep moving with a higher velocities, and hence they gain heat, they receive the heat energy, and the temperature increases because RMS velocity of the molecule and temperature of the molecule are interconnected. So high temperature molecules or high velocity molecules transfer their energy to the low velocity, low temperature molecules during collisions by momentum transfer. So the low temperature molecules receive the energy and keep moving with the higher velocity. That energy is transferred to the low temperature plate. So that is how the heat energy is conducted inside the gas. But gases are poor conductors of heat, very poor conductors of heat. For example, air. Air is a better conductor. It is a better conductor. It is a better insulator. I can rather put it that way. It is a better insulator than many of other solid insulators like wood or etc., like wood or rubber, etc. If metals are good conductors of heat, there are bad conductors. There are bad conductors of heat called insulators. For example, rock wool, wood, asbestos. Asbestos is a very prominent practically used insulator. Glass wool, etc. Gases are also very bad conductors of heat. For example, air. The heat conducting ability of a material is given by the property called thermal conductivity. Very important property which we use extensively in the subject, thermal conductivity, K, having the units of watts per meter degree centigrade or watts per meter Kelvin. Among all the materials, silver is the best conductor of heat. Example, K of silver is 405 watts per meter Kelvin. Now I would list out in the descending order of conductivity. Top is silver, next is in line is copper, next in line is aluminum, steels, etc., some other conducting metals, and the other extreme we have rock wool, wood, asbestos. Even air is a very bad conductor of heat. Silver is 405, copper is 385, aluminum is roughly 200, steels vary between 15 to 45, all are in watt per meter Kelvin, whereas air is very low, 0.07, very low. Even the water has got slightly more, 2 to 6 watts per meter Kelvin. Water, which is a better conductor than air, will have a slightly more thermal conductivity, definitely more than air. Liquids are also conducting ability, have got the conducting ability of heat. So we had seen what are the best conductors, what are the worst conductors, like which are also called as the worst conductors of heat are also known as insulators. Now let us move to the second mode of heat transfer called as convection. In this phenomenon of convection heat transfer, heat is supposed to be transferred from a hot solid body to surrounding fluid. So whenever a hot solid body is kept in a still air or in the moving air, heat is said to be convected from the solid body to the fluid. The fluid may be air or a water. As we have seen practically also, if a high temperature body is just kept in the still air, after certain passage of time that would reach thermal equilibrium condition with the surrounding atmosphere, that is equality of temperature, where the further heat transfer ceases or stops. So I say heat has convected from the solid body to the surrounding fluid. In fact, the process may be even reversible. That is, heat may be gained from the fluid to the body because of temperature difference. If a hot fluid is blown over a solid body, heat is convected from the fluid to the body. Heat convection is a very natural phenomenon from the human body to the surrounding ambient air, because human body is at a temperature of 37 degrees centigrade. If you sit in a tub of water, cold water, we will feel that the heat is being lost from our body to the surrounding water by convection. We feel chilled. If you sit in front of a fan, we feel that heat is convected from our body to the surrounding air. So I can say that convection heat transfer is the mode of heat transfer which generally occurs between solid body and the surrounding fluid due to temperature difference by macroscopic displacement of fluid, that is in the case of forced convection or by microscopic motion of fluid, or by macroscopic motion of fluid which occurs naturally by density differences arising out of temperature change and the resulting buoyancy forces. That is, in the case of free or natural convection. So I can say that convection is a mode of heat transfer which occurs between a solid body and the surrounding fluid by macroscopic motion or the displacement of the fluid. That is the difference between the conduction and convection. In the conduction, the molecules would not leave their space, would not leave their mean positions, but they would be transferring energy to the neighboring molecules by molecular lattice vibration and also by free electron transfer. But in the case of the convection heat transfer, there is macroscopic displacement of the fluid, which may be provided externally by an agency like fan or a blower or a pump in the case of the water. And this macroscopic motion of the fluid might happen naturally due to density differences arising out of temperature changes, particularly in the case of the natural convection or free convection heat transfer. So I can classify the convection heat transfer between forced convection and free convection. Now let me represent pictorially the forced convection and free convection. Hot solid body. This is a fan blowing air over the hot solid body. There is a boundary layer development over the plate. I would elaborate what is a boundary layer later. And heat is convected through this boundary layer from the solid body at TW to the air at T infinity temperature. If the hot solid body is kept in a still air or like a hot wall, the surrounding still air would receive that energy and the temperature of the air increases, hence density decreases. So here also there is a boundary layer development because the hot air is lighter and keeps moving upwards. Here TW is greater than T infinity. If the TW is lesser than T infinity, like this is a cold wall, the more displacement of the air would be like this, because air gives the heat. T infinity is greater than TW. Air gives the heat to the wall and the temperature of the air decreases. It is a still air, stagnant air or a still air, and the temperature of air decreases, because of which the air gets displaced downwards. Because density increases as the temperature of the air decreases and it flows down inside the boundary layer. So in the forced convection heat transfer, the motion is assisted by an external agency like a fan or a blower, whereas in the case of free convection heat transfer, the motion occurs naturally due to the density differences and hence the resulting buoyancy forces. I can put a hot sphere kept in a still air which gets displaced. The air gets displaced in this fashion. Cold air, this is hot sphere, and the displacement of the air is shown in the form of the arrows. If this is a horizontal plate, hot plate, if it is kept in a still air, the displacement is like this. So all these examples are all the examples of free convection heat transfer, except the first figure. First figure is the phenomenon showing forced convection heat transfer. Naturally, the rate of convection heat transfer would be more in the forced convection than in the free convection. Now coming to the third mode of heat transfer called radiation. In the earlier modes of heat transfer, namely conduction and convection,